In this video, we are going to look at inverse functions. And here at the top, I've shown graphically what inverse functions look like on the coordinate plane. So, excuse me, if two functions are inverses, then they're reflections of each other about the line y equals x. So we have two graphs here. The first graph is y equals e to the x. We haven't talked about that yet, so that's okay that you don't know how to graph that. And y equals the natural log of x. Again, we haven't talked about that yet. But notice that the line y equals x is dashed in here. And notice that we see symmetry about that line. So these two functions here are inverses of one another, and they are symmetric about the line y equals x. Also over here we have f of x equals x to the third, and then also the inverse function, which is the cube root of x. Notice this notation, we'll talk about this later, this f inverse of x. And again, you can see symmetry about the line y equals x. Another way to look at, or another way to think of it is if the point xy is on the graph of f, then the point yx would be on its inverse g, or f inverse of x. These two functions here are inverses. Notice that the point 1, 2 is on the graph of f, and then the point 2, 1 is on the graph of g. I'm going to talk about this more later. This is actually a way that I will check my work when I find inverse functions. So this is kind of a great way to check your work. It would have to work for all points, but if you find one and it works, there's a pretty darn good chance that you've done it correctly. Last thing before we do the math involved, not all functions have inverses. They have to be one-to-one, and a way to check to see if a function is one-to-one is to see if it passes the horizontal line test. Now, we've talked about a vertical line test. A vertical line test will determine whether we've got the graph of a function. But the horizontal line test will determine whether a function has an inverse. So the example given here is f of x equals x squared. That's a parabola if we were to graph that, and it would not pass the horizontal line test. Wow, that's supposed to be a horizontal line. It's a little not very straight there. But anyway, if I would draw a horizontal line, it's going to intersect the graph in two places, not just one, which would mean f of x equals x squared does not have an inverse. So our parabolas that open up and down do not have inverses. Okay, so here is the process that we're going to follow to find an inverse function. We're first going to replace f of x with y. This is just going to help us with the next step where we're going to swap the positions of x and y. You could keep it as f of x, but it's kind of tough to switch the positions of x and f of x. It's kind of easier if they're both just, just a single variable, although f of x technically is just y. Then we're going to solve for y in its new position, and then we're going to replace y with f inverse of x. Here's the notation here that we use. It kind of looks like an exponent of -1, but we say that f inverse of x. Okay, here we go. So step 1, that first bullet point says to replace f of x with y. So I'll have y equals 5x plus 15. All right, then we're going to swap the positions of x and y, and we take nothing with them, no coefficient, no exponent, anything. So you're just going to completely swap the positions of x and y. And then we're going to solve for y in its new position. So to isolate y in its new position, I would subtract 15 from both sides. This means x minus 15 is equal to 5y. Then I'm going to divide both sides of the equation by 5. Okay, I'm trying to isolate the y. And so x minus 15 all over 5 is equal to y. Now remember that we cannot reduce here because I can only cancel factors, not terms, or I can only reduce factors, not terms. If you want to split this up, you can, but it would end up being 1/5 x minus 3. So I'm taking each term in the numerator and individually putting it over the denominator. Okay, now you don't have to do that. You could also leave it like this. Now the last thing I'm going to do is I'm going to use this notation here. F inverse of x. Sorry, this doesn't look very good here. Like I said, it really just looks like an exponent of -1. There we go. And this is equal to 1/5 x minus 3, or like I said, feel free to use the x minus 15 over 5. That works as well. Now, I mentioned that I do have a way to check. So what I do to check is I find a point on F. And to find a point on F, I just pick an x value. It really doesn't matter. Pick any x value you want. How about 1? 1 isn't too bad. Okay, so pick an x value. Plug it into the function f. So find f of 1. So I'll show this down here. So I'm going to find f of 1. So this would be 5 times 1 plus 15, and that's 20. So what that means is the point 120 is on the graph of f. Now, if these are truly inverse functions, then the point 20, 1, so I reverse the coordinates, okay, because inverse functions are reflections about the line y equals x. So if the point xy is on f, then the point yx, or in this case 20, 1, should be on the inverse function. So we need to figure out, is 21 on f inverse of x? Okay, so let's check this out. And don't know what happened there. Okay, so let me move this down a little bit here. I'll show it on the next page here. Okay, so let's see. I'll even write this down. Is 21 on f inverse of x? Okay, so let's see. Let's plug it in. So I'm going to find f inverse of 20. And I'm going to plug 20 in for x. And 1/5 times 20 is 4. And 4 minus 3 is 1. So sure enough, it is. 21 is on the graph of f inverse of x. Okay, now this isn't a guarantee that you're correct, but it's a great way to check. It would be really strange that you happen to pick, a point that, xy is on f and yx is on f inverse and then be wrong. It would be, I guess it could happen. 1 in a million, I guess. Okay, but there's a pretty darn good chance that if you find a point on the graph of f and then take, reverse the coordinates, so then take yx and plug it into the inverse function, if it works, there's a really good chance that you are correct. Okay, let's see another one. So we have h of x equals x plus 6 over 2. So step 1 is to replace f of x with y. Now in this case we have h of x. So same thing though. So we're going to just make this y equals x plus 6 over 2. Then we swap the positions of x and y. You take nothing with them. and then we solve for y in its new position. To solve for y in its new position, let's first multiply both sides of the equation by 2. That will allow me to cross cancel there. So we have 2x is equal to y plus 6. I'll subtract 6 from both sides, and 2x minus 6 equals y. Okay, now if we want to then use our fancy notation here, now this function is h of x. So our notation here would be h inverse of x instead of f inverse of x, since our original function was h of x. So h inverse of x is 2x minus 6. All right, and this is our answer. Now I'm going to do the same thing. I'm going to do a quick check here. So this is the way I like to check to see if I've done this correctly. So I need to find a point on the original function. How about I pick 0? That's a good one to plug in. 0 isn't too bad. Okay, so I'm going to find h of 0. And h of 0 would be 0 plus 6 over 2, which would be 6 over 2, which is 3. So this means that the point 0, 3 is on the graph of h. Okay, now if this here is truly the inverse of h of x, then the point 3, 0, so I'm reversing the coordinates, should be on the graph of h inverse of x. So let's see if it is. And by the way, remember, I just pick 0 randomly. Pick whatever you want as your x coordinate. Then you plug it in to figure out the y coordinate, but pick whatever you want to start with. Okay, so we want to know, is 3, 0 on the graph of the inverse function here? All right, so let's test it out. So I'm going to find h inverse of 3. I'm going to see if it's 0. So 2 times 3 minus 6 is 6 minus 6, which is 0. All right, so, you know, we're not 100% sure we're right, but we're like 99.9% sure that we have correctly calculated the inverse function. Okay, a couple more here. Now we've got some exponents, and in the next one we'll see what to do with a radical. Okay, so I'm going to follow my steps again. First step is replace f of x with y. Swap the positions of x and y. Remember that we take nothing with them, not even exponents. Okay, so you just completely swap the positions of x and y, and then we solve for y in its new position. I'm going to add 2 to both sides. Then, excuse me, we need to get rid of this coefficient of 3/4. And to do that, we're going to multiply both sides of the equation by the reciprocal, which would be 4/3. That way, I can cross cancel the 4s, and I can cross cancel the 3s, and therefore I've just got y to the 5th. So I'm trying to isolate the y, and so to get rid of that coefficient, I'm going to multiply both sides of the equation by 4/3. Now, you're welcome to distribute on the left side if you'd like, or not. It's completely up to you. I guess I won't distribute. I'll just leave it as 4/3 times the quantity x plus 2. And this equals y to the 5th. Okay, now to solve for y, now we've got y to the 5th isolated, but we want to know what does y equal. We're going to take the 5th root of both sides of this equation. Sorry, that didn't turn out very good. That's supposed to be a 5 there. And when you take the 5th root of y to the 5th, that's just y to the 1st. Okay, so our equation becomes y equals the 5th root of 4/3 times the quantity x plus 2. Okay, and then I'll change that to f inverse of x. Okay, this shows that this is the inverse function of f. We've got this. Sorry, my 5s are really not working that great. Now, technically, we should rationalize this denominator. This is the same thing as the 5th root of 4 times the quantity x plus 2 over 3. And as we saw in the first unit, we always want to rationalize the denominator when we've got a radical down there. But we're not really going to worry about that in this section. It's kind of tough too when you've got a 5th root down there. So anyway, we're going to go ahead and call this our answer, although I do want to point out that technically this isn't the best answer we could get because we have not rationalized the denominator, but that's okay. Okay, one more problem in this video, and then there is a second video on inverse functions, but with rational functions. So I didn't put any rational functions in this video, but check out the next one because rational functions, they're a little more difficult, I guess, to find the inverse. All right, so first thing I'm going to do is I'm going to replace g of x with y. Then I'm going to swap the positions of x and y, take nothing with them. And then now we're going to solve for y in its new position. The first thing we'll do to isolate the y is we need to isolate the radical first. And so we're going to divide both sides of the equation by 2. It is divide because it's 2 times that radical. So division, the opposite operation, is going to isolate this radical here. So that way I can cancel my 2's. So we have x over 2 is equal to the 7th root of y minus 5. Okay, then this one's a little bit different than the last one, but similar. Now we've got a radical. So we want to get rid of a radical. We're going to raise both sides of the equation to a power that is the index of the radical. So raising both sides to the 7th power is going to get rid of our radical. So on the left, we have x over 2 to the 7th. You can leave it as x over 2 to the 7th like this in parentheses, or if you want, you could also raise both the numerator and the denominator to the 7th power. 2 to the 7th power is 128. Okay, and then when you take a 7th root and raise it to the 7th power, you get rid of the radical, and we just have y minus 5. Okay, the last thing we're going to do is we're going to add 5 to both sides of the equation because we're trying to isolate the y. And so, let's see here. Sorry about that. Let's see if I can get, I'm just going to move all my work down. Oh, well, okay. I want a little bit more room here. Moved everything down, but that's okay. Okay, so we have y equals x to the 7th over 128 plus 5. If we want to use our fancy notation here, now the original function was g of x. So g inverse of x would be this here. And I do want to caution you because, and let me put a box around this because this is our final answer. I have some students that will do this. Okay, so this, I'm going to say this is bad. Don't do this. Some students will do this. They'll take that 5 and for some reason they'll add it in the numerator. That's not, don't do that. It's just added. Now, if you want to make it a single expression like this, then you're going to need a common denominator. Okay, so you need to, make this 5/1 and then multiply both the numerator and denominator by 128. Okay, so don't do this. Okay, not equivalent to that. So just keep your +5 there in the back. Okay, or find a common denominator. All right, well, thank you for watching this video. And like I said, there is another video on inverse functions with rational functions. And in that video, I also talk about the domain and range of functions and their inverses.